Lecture 24. In this lecture, we're going to talk about vapor pressure. So what is vapor pressure? Well, vapor pressure is the pressure of the gas above a liquid. Okay, vapor is a gas, so it's the gas above the liquid. So here it says when molecules leave the surface of a liquid to enter the gas phase, they exert a pressure. Remember, in a liquid, technically we're not going to talk about its pressure, but when it turns into a gas, it's going to have a pressure because it's going to fly around and hit the side of the container. So the vapor pressure is the pressure exerted on that gas, and the rate, and it's dependent on the rate of evaporation. So if the rate of the evaporation is fast, then we're going to have a high vapor pressure because now we're putting more gas into the air basically. So if the rate is slow, then it is low pressure. Okay. Also, the rate of evaporation is also dependent on temperature. So if you have a higher temperature, you're going to have a higher rate of vaporization, which means you're going to have a higher vapor pressure. Okay, so make sure you understand that. So high temperature, high evaporation rate, high vapor pressure. So let's take a look at this. This is vapor pressure in an equilibrium. Now let's say we have a closed container. So if this was at room temperature, most of the water will be in liquid form, but some of the water will have enough energy to basically become vapor. Okay, so basically it's going to become a liquid. So it becomes a liquid, and some of them will lose its energy and fall back down into, or create a liquid again. But then some will gain energy to increase into become a vapor. And this process continue, and we notice that this process is an equilibrium process. So the amount of vapor that is being created is the same as the amount of vapor that is being returned back into liquid form. As we increase the temperature, okay, we're going to increase more vapor, and because we have more vapor going in, we're going to have more vapor coming out also. Okay, so we're going to have that. So the rate of evaporation is equal to the rate of condensation. We would have an equilibrium situation. Now, there's something called boiling point elevation or depression. Okay, so we see this. If I go to Denver, which is a mile high up in the Rockies Mountain, okay, the water up there boils at a lower temperature than the water down here. Well, why is that? Well, that's because of atmospheric pressure. Okay, so what happened is when the liquid boils, okay, when water boils, we say that vapor pressure is equal to atmospheric pressure. So on sea level, when water boils, then the vapor pressure is 1 atmosphere because it's equal to the vapor pressure of the atmosphere. I'm sorry, the pressure of the atmosphere. So it's 1. But if we go up in the mountains, like in Denver, the atmospheric pressure is going to be lower. So to get enough heat to boil water, you don't have to bring it up to a temperature of 100 degrees. So you can actually boil water at a lower temperature up in high elevation because you don't have to get to 1 atmosphere. You can get to like 0.8 atmosphere and it will start to boil. So if we look at this, you know that at sea level, water boils at about 100 degrees Celsius. In Boulder, Colorado, which is up in Denver, a mile up in elevation, it boils at 94 degrees. In La Paz, Bolivia, which is pretty high up, almost 2 miles up, it basically boils at 87 degrees. Now, if I go up to Mount Everest, okay, which is way up there, okay, it boils at 70 degrees Celsius. Now, even though water boils at 70 degrees Celsius, it's going to cook my food longer. It's going to take longer to cook my food because even though it's boiling at 70 degrees Celsius, it only contains 70 degrees of energy, right? Of kinetic energy per se, right? We convert that to kinetic energy. So basically, even though it's boiling, it's not hot enough to cook my food. So my food actually cooks longer, have to be cooked longer at high elevation than it would be if I had basically at lower elevation. So now, are all boiling points the same for every liquid? Well, the answer is no. The vapor pressure of a liquid is dependent on the intermolecular forces that are holding that liquid together. So if a liquid has a strong intermolecular force, then the vapor pressure above that liquid is going to be pretty low because you're going to need a lot of energy to vaporize. But if the intermolecular forces of those liquids are weak, then you have easier way of basically vaporizing that. So certain compounds like alcohol tend to have very low intermolecular forces. That's why if you take a little alcohol, put it on the ground, it evaporates very fast. Water is pretty high, but still it can do it. But there's other substances that the intermolecular forces between the molecules are very strong. And because they're very strong, it takes a lot of energy to vaporize it. So the boiling points of those substances tend to be very high, and the vapor pressure tends to be very low above things that have strong intermolecular forces. So if liquids have strong intermolecular forces, then the vapor pressure is going to be low. If the liquid have low intermolecular forces, then the vapor pressure is going to be high. So if you look at this list, it shows you this, right? So if you have liquid argon, and liquid argon is a nonpolar substance, so all you have is dispersion, London dispersion forces. Notice the the heat of vaporization, okay, and the boiling point very low. So there's not a lot of forces holding together. Now CH4, okay, also has London dispersion, but remember it's bigger, it's heavier than argon. So notice the higher one. C6H6, again, it only has London dispersion forces, but because it is heavier, it has more polarization possibility, okay? It has a higher delta H of vaporization because the intermolecular forces are a little stronger. Now water has London dispersion forces, but it also have H bond. And because of that, its intermolecular forces are very strong. So that's why the delta H of vaporization is very high, and the boiling point is also high also. So again, what's the connection? It's intermolecular forces. The stronger the intermolecular forces, the higher the boiling point, the higher the delta H of vaporization. Okay, so again, the higher the intermolecular forces, the higher the delta H of vaporization, the higher the boiling point. And the opposite is also true.